Okay, so this will be our video that is a continuation of lesson 19, which is how to calculate the area on a polar graph. And what I have here is the generic scenario that we have a polar curve or a graph or whatever you want to call it. R will be a function of theta, kind of like this problem that I'll do here in a minute. What if R was cosine theta? R is a function of theta, meaning you plug in the angle is the input, and then you get R, the radial coordinate for the polar coordinates. And you plot all those points and you get some kind of a curve. That's what R is equal to f of theta is. And so the scenario is to find the area radially within that curve between these angular boundaries, or radially within the curve within this angular wedge between angle A and angle B, whatever those are. Okay, so it's not the area under the curve, it's not the area to the left of it. As I said, it's the area radially inside of it, where the radial direction is from the origin directly outward. Okay? Alright. So if you wanted that area, then it's the definite integral from angle A to angle B. 1/2 is this universal factor in these integrals, r squared d theta. So theta will be the variable in the integral. Okay. Now, so let's see a problem. Okay, so we have our lesson that we have been working on. This one's not in the lesson, so this is something I made up. But I wanted to give you a tangible example of that thing that you see up there. Okay, so say we have this question that is as follows. Calculate the area radially within the graph of cosine theta from 30 to 45 degrees. So here's a scale picture that I drew with my circle template and my protractor. So that's real life, that's what it looks like. And it's, you know, just think of that picture up there, the area radially within this curve. See that deal right there? This circle is r is equal to cosine theta. Okay, sure enough. There's this little arc that is contained by those angles, and here's the area radially within it. So that's shaded. So suppose that I want to measure that somehow. Okay. All right. So let's. Oh, real quick about why. How do I know this is the graph? Well, hopefully we're at the point where we can draw graphs of things in polar coordinates. There's lots of ways you could do that. You could make a table. You could convert it to x and y coordinates and see that it's a circle that has a center of 1/2 on the x-axis, and it has a radius of 1/2. You might note that that point in polar coordinates, r and theta, is 1 and 0 degrees, because isn't it true that cosine of 0 is 1? And, all right, cosine of 90 is 0. That's this point right here. But you know, that's what it looks like. If we need to discuss how to draw the graphs, and we can do that some other time. But that's what we have. So let's do like this. So you see this area that I have indicated there, then that will be, remember our setup, remember our equation up there. So it's going to be, let's do, really doesn't matter if you put these bounds in degrees or radians. You just do the math anyway. Cosine of 30 degrees is no different than cosine of pi/6 radians, so it doesn't really matter, but I'll stick with the convention and I will put this in radians. Okay, so I got the integral from pi/6 to pi/4, 1/2 r squared, so r is cosine, so cosine squared, theta, d theta. Alright, so that's what we're up against this time. Now, here I'm going to, you know, I guess we could work every integral from scratch like we've never seen them before. but you know, we have seen this kind of thing, and there's a certain identity that you use for cosine squared in such an integral, and it's going to be 1 plus cosine of 2 theta over 2, but I already have a factor of 2, so I'm going to put 4. Okay, so continue. Now, I see this as two separate terms. I see it as a 1/4 and plus a separate term, cosine 2 theta over 4, whose antiderivatives would be theta over 4, plus, by perhaps use substitution, sine 2 theta over 8, because the derivative of sine 2 theta is cosine 2 theta times 2. Cancel with 8, get cosine 2 theta over 4. Alright, I'll take that from pi over 6 to pi over 4, or 30 to 60 degrees. Alright, when you do sine 2 theta, same thing. Alright, so I said, well, we could use degrees or radians, because sine of 30 degrees, or whatever that angle is the same as sine of pi over 6 radians, but I get the convention to use radians. It becomes important here. You know, of course, obviously, we're going to get a different answer if we put 30 degrees divided by 4. You know, instead of pi over 6 divided by 4. Obviously, different things. Well, if we want to calculate the area, we have the convention. We use radians because it might work fine there to put degrees versus radians in as long as you do your math correctly. But here you get something different. So use radians, alright? We have the convention to use radians for that reason. So anyway, pi over 4 first, I get pi over 16. And then here, 2 times pi over 4 is pi over 2, sine pi over 2 is 1. So I get 1 over 8. Alright. Pi over 6, so I get pi over 24. Alright. And then here, I'll get sine, so 2 times pi over 6 is pi over 3. And so that amounts to basically 60 degrees, right? Which is root 3 over 2. So I'll get root 3 over 16. Okay. Putting pi over 6 right there. I end up seeing pi over 3. Sine pi over 3 is root 3 over 2. Sine of 60 degrees is root 3 over 2. So either way, I calculate root 3 over 2 over 8, so I get to 16. So, alright, so let's see where we can take this. Pi over 16 and 24. Common denominator, so let's see, out of that, this is 2 to the 4th power, 2 times 8, 3 times 8. Let's add those together. We'll put it over, we can do 48, okay? So 3 pi over 48 minus 2 pi over 48. So I'll get pi over 48. And then 1 over 8 plus, or sorry, minus root 3 over 16. Well, those aren't really like terms. I can't combine a 1 and a root 3. But I guess I could do something like this. If I got, say, both of those over 16, I guess a 2 over 16 minus root 3 over 16. So let's go ahead and say something like 2 minus root 3 over 16. So that's kind of an ugly answer, but that does sometimes happen in math. Alright. 5 over 48 plus 2 minus root 3 over 16. And we have units. We have square units. This is a measurement of area. Okay? Alright. Anyway, let's take a good look at that. So there's our answer to that little, very small piece, very kind of weird looking wedge piece with the reference to polar coordinates of that circle. I'm kind of curious to see what that number is. We'll give the exact answer when we do things in class or on the test or on the lesson. But I am interested. say take pi over 48 plus, and I'm going to do 2 minus root 3 over 16. Okay, so I get like not very big, 0.082, so about 0.082 square units. Okay, so not very big. Kind of curious, like, what's the area of the entire circle? Alright, so just as a comparison, because sometimes through doing this we might need to find the area of a circle, so let's go ahead and examine this, and I'm kind of curious to compare with that number. So let's see, area of this entire circle, it has a radius of 1/2, right? This diameter points over at 1, so the diameter is at 1. So the area of the entire circle is pi times 1/2 squared. Okay, pi r squared. That's how you find the area of a circle. And so that's going to be pi over 4, which is about 0.75 or so. It's about 3/4 pi over 4. It turns out to be 0.78, 0.79. So the whole thing is only about 0.79 square units, less than the size of a 1 by 1 square. If I had a square that was 1 by 1, it's like 79% of that. Well, that little piece, very tiny piece, less than 1/10 of a square unit. Okay, that's what fraction that little piece is of the entire circle. Okay, so there's the first problem. As long as I took to do that, it really just meant to be a warm-up of seeing how this could play out. Now let's do one from the lesson. So here's what would be question, at least at this time. This would be question 7 from the lesson, and it says as follows: calculate the common area within both graphs, r sine theta and r is cosine theta. So there's what they both look like. They're both circles of radius of 1/2. We were just looking at this one, in fact. And there's r is equal to sine theta. Also circle radius 1/2. Center is at 1/2 on the x-axis. So that would be a 1. This would be 1/2 on the x-axis. That would be a 1. And I suppose that the common area in both of them at the same time is that. Okay, I want to find some way to measure that. All right, that's the idea. Now, all I have to go on is, this is the generic problem. That that's all I have to work with, is that this is how things are done. Okay, and what I notice, if I describe this as the area radially within the curve r is f of theta between angle A and B, then this region is not radially within either exclusively sine or cosine. Like, part of it is radially within sine, and then part of it's radially within cosine. See? Alright. So that seems a little strange. I think here's what we're going to have to do. I noticed that, like, this angle here, that gets this intersecting point. I noticed, like, that seems important. Alright? Okay, so yeah, it does. And if you go from 0 to whatever that angle is, your area is radially within this arc, which is r is equal to sine theta. But if you go from this angle to 90 degrees, then that area right in here is radially within this arc, which is r is equal to cosine theta. Now that does cut it right in the middle, so I guess we could find one or the other of those and then just double it and get the whole thing. Now I did take advantage of drawing this to scale, and Those are circles of the same size, just as they are in the problem. And so I'm gonna cheat a little bit for now and say that angle is 45 degrees. Okay. All right. So let's say pi over 4. Okay, 45 degrees. So you could do like this. You could say from 0 to 45, you're radially within sine. From 45 to 90, you're radially within cosine. So take your pick. Just find one of those. Find what appears to be the lower half or the upper half, and double it. You get the whole thing. Okay, so I'll set it up like this. That total area that you see by symmetry is going to be double. I don't know. It seems a little easier to use 0. All right, so I'm going to say this angular wedge that contains the area I'm trying to measure is 0 to pi over 4. Yeah, this piece, the lower piece, where you're radially within sine. So I'm going to say 0 radians to pi over 4 radians. Okay, double it for the sake of symmetry. 1/2 r squared being sine squared d theta. Okay. All right, so we got that. That'll do it. That'll do it. So can we agree that despite whatever happens next, as far as us having to work it, do the math, that this would get you all of that area that I had originally shaded before I put any angles on the picture? Okay. So we will get. Let's do a few things at one time. So I get 0 to pi over 4. The 2 and the half will cancel. So that's why we do like to use symmetry when we can. Sine squared, we're going to have to say, is 1 minus cosine 2 theta over 2. Alright? That's what will work. That's the way we always do that kind of thing. And this is a 1/2 and then minus, separate term, cosine 2 theta over 2. So I'm going to get, for an antiderivative, theta over 2, the antiderivative of 1/2, minus sine 2 theta over 4, the antiderivative of cosine 2 theta over 2. Okay, so that's going to be from 0 to pi over 4. So I will get pi over 8, and then minus 1/4. Okay, so pi over 8 minus 1/4, man, that's as good as it gets. 0 is not going to give me anything. 0 over 2, sine 0. So I'll just get this. I suppose, that's fine. Okay, if you really feel inclined to say something else, or I don't know, if you're using a book or you're doing problems somewhere else and you look up the answer, sometimes you see something a little bit different than what you got. You could say that these could be combined out of 8 and common denominator 8, giving me pi minus 2 over 8. Alright, either way, I'm not sure which one is in the lesson, but can we at least agree that it's the same? Alright, there we go. Okay, so that's how we do 7. I have to think about the setup, right? I mean, this first problem, it's really just given to you. I wanted to draw it so you could see what it looked like, but it's not like you have to do that. You know what's going on. Here, though, it would be hard to figure out how to set that up if you didn't know what those look like together. And if you didn't have that picture, it'd be hard to understand the symmetry aspect of it. Okay. Now, let's talk about something. I cheated a little bit, and I said that angle would be 45 degrees. I actually didn't do any math to get that. I made a perfect drawing, and then I measured the angle. But that angle would be the point of intersection. Okay? And so maybe we should discuss how you find that in case you don't make such a nice drawing and you can't take advantage of measuring it. point of intersection. See how these two things intersect right there? Like, how do we determine the angle that indicates where that point is? You know, how do we know that it's pi/4 if measuring is not an option? Well, at this point where these two things intersect, you can say they're equal. Okay? So you have to extract some kind of answer out of sine theta equals cosine theta. So here's the way that I think you could do it. I mean, as far as solving it, I think the solving procedure is a little bit complicated for that. So how about we just see if, from our awareness of common angles, if there is an angle where sine and cosine give you the same answer, and that is 45 degrees. Okay? Sine of 45 and cosine of 45 are both 1 over root 2. That's one answer. It's not the only answer. They also give you the same thing at 225. Okay? But, you know, obviously 45 takes you there, and it's easy to verify that you both get 1 over root 2 for the radial coordinate, and that's where that point is. This point is rotated 45 degrees, and it's a distance of about 0.7 to get to right there. 1 over root 2. Okay, so you define points of intersection or the angles therein. You'll have to set the two equal to each other and solve it, or find the solution one way or another. Okay, all right. So let's go on to the next thing. So if I do the problems that come after this, they'll say it will come down to something like this: calculate the area radially between two curves. So we can find the area radially within a curve, like that, or between them, like maybe outside of one and inside of another. You know, here's like curve 1, R1, curve 2, R2. Find the area radially between them, not under one and above the other, or left and right, but radially between. Okay, radial direction being directly out from the center, as I always say. So something like that. Okay. Now, all right, that would be by this formula. It looks kind of like our other one. Integral a to b 1/2 r2 to curve this radially further away squared minus r1 to curve this radially closer squared d theta. Where's that come from? Well, it's like this would give you all the area in this wedge radially within the curve r2. But if we want the area between them, then we subtract the area within the closer one. You know, so you took all this here and you subtracted all this right here. Wouldn't it leave that shaded part left over? Well, that's what this is. I mean, but this turns into that. So okay, let's just, you know, if you wanted a reason for this, that'd be my reason. But we'll just use this. We won't think through it every time we use it. Okay, so there's our new scenario. Let's see an example. All right. So this one says, this is question 6 from the lesson, at least at this time right now, that is question 6. Calculate the area inside r is equal to 1, but also outside r is equal to sine theta. And here they both are. R is equal to 1 is a circle who has a center at the origin and has a radius of 1. So it's the larger circle. R is equal to sine theta is, well, we've seen that elsewhere already, but it's a circle that has a diameter of 1. So actually, it meets this other circle right there at the polar point, as in polar coordinates, r and theta. 1 for r, pi/2 for theta. That's what they look like. Okay? So how about this? Like, the area inside the one and outside of the other, that's going to be like all this down here, all that, right? Okay. Now, at this point, I ask you to remember something in class. I said that I can give you a scenario, but I'm going to let you figure out the best way to work it. And so we could use calculus, obviously. Or maybe we can find an easier way. So let's do this. Like, I think I'm kind of struck to find an easier way right now. So let's say method 1 with no calculus, because calculus is hard to do and we avoid it when we can. All right. Okay, so wouldn't the area I shaded just be, let's see, I'm gonna write this down. Pi times 1 squared minus pi times 1/2 squared. Yeah, that would do it. Because this big circle has an area of pi r squared with radius being 1. And if you just took away the little circle inside of it like that, you get the shaded part left over. The little circle, the r is equal to sine theta, has a radius of 1/2. So we get, oh, it's going to be easy. Pi minus pi over 4. So in other words, 3 pi over 4 square units. Okay. Alright. So that'd be an easy way to do it, I think, if you're aware of it. But it's like true with me and true with anybody else. The easy way to do it might be right in front of you, but you don't see it. And so we learn to use calculus. Alright? Well, sometimes we have to use, sometimes there's just no simple way to do it. Okay? Alright, so sometimes either because we're not very clever, we have to do something more complicated, or because it's just not possible to do it easily. Okay, so method 2, I'll use calculus. I'll show you how that this is in some ways the area radially between two curves. Alright? And here's how I'm going to set it up. Let's say that we call, let's do like this. I'm going to call B this region underneath right there, which is a semicircle. I'm going to call this area A over here. Okay? So in other words, like A is like all this stuff right there. And then B is all this right here. Wouldn't the answer be B plus 2A? Yeah, I think so. Okay. And why set up like that? Well, because the space B down there doesn't really seem like, if we look at it, we probably won't think it's the area radially between two curves, like where the curve r is equal to 1 is radially further than r is equal to sine theta. At least it doesn't look like that. So B is just, okay, half of the area of the circle that has a radius of 1. So that's going to be, B will be pi over 2. Okay, now let's find A. Okay, so how do you find area A? As I have drawn it up there. See that deal? Okay, well, that is the area radially between the curve r is equal to 1 and r is equal to sine theta. R is equal to 1 is radially further out than r is equal to sine theta, and this is the space between them. So what are the angles? Wouldn't it be, let's see, we always make sure we identify the angles correctly. Here I think it's easy. Theta is 0 degrees over 2, theta is 90. Maybe that's so obvious I shouldn't have even written it down. But the wedge that contains area A between 1 and sine theta is 0 to pi over 2. Okay. Alright. So then we do 1/2, and what was that formula? Take the curve that's radially further away and square it. That would be r is equal to 1 minus the curve that's radially closer, sine squared. and square it. So sine squared. All right, that's further, that's closer in a radial direction. That's that formula. Okay, so we're going to get then, let's see, let's do like this. I'll just leave the 1/2 there. I'm not worried about it. 1 squared is 1. But the sine squared, okay, well, we got to, oh, let's do this. I got an idea. So if we're going to do it this way, we're going to use calculus. 1 minus sine squared, that's cosine squared. This will be easier. I'll take advantage of that. Well, the easiest way to do it would be like that. But let's say that we're using calculus. Just to practice it, because that might be how we end up doing it. Alright, so I'm going to say 1 minus sine squared, that's cosine squared. And then I'm going to say, as I have done in a problem previously in this video, that's going to be 1 plus cosine 2 theta over 4. And I'm going to have antiderivative of theta over 4 plus sine 2 theta over 8 from 0 to pi over 2. Okay, so for pi over 2 in there will give me pi over 8. And then pi over 2 here. If I multiply by 2, I get pi. Sine of pi is 0. And then 0 in here gives me 0. And again, I just get pi over 8. Okay? Alright, now, so that is area A. It's pi over 8. So see this deal. That's pi over 8 in terms of its area. So, okay, to get all that shaded area, I wanted 1b and 2 a's. So let's do plus 2 times pi over 8. So that's going to be pi over 2 plus pi over 4. Okay? With some canceling. And if we get a denominator of 4, we'll get 2 pi over 4 plus 1 pi over 4. So we'll get 3 pi over 4. That's area. So I put units of area measurement right there. Right, of course, the same answer, 3 pi over 4. Something's not right if we get 3 pi over 4 this way and 3 pi over 8 this way. Obviously made a mistake somewhere. 2 alternate methods to measure the same thing, get the same answer. So anyway, all right, now take your pick. I hope you would realize and pick the first way to do it, but well, we need to know how to do this anyway. At least now, as you watch this, I hope that you identify what I'm calling area A, and you can agree with my setup right here to measure it. Okay, at the very least, that's what I want you to get from doing this one. Alright, so let's try a few more from the lesson. So 9 here. Calculate the area inside R is 4 sine theta and outside R is 2. Well, so there you have it. That's what they look like together. They're actually both circles of the same size. This one has a radius of 2. And let's say that we kind of take for granted that R is sine theta, R is 2 sine theta, R is 4 sine theta. They are going to be circles with centers on the y-axis somewhere. So why do I think that they're the same size? Let's see, where's this point? See that point right there? Like just for reference. That would correspond to an angle of pi over 2. Sine pi over 2 is 1, and so R would be 4. So I'll get, for R and theta, I'll get 4 and pi over 2. So if that one has a radius of 2 centered at the origin, and now this one has a diameter of 4. Okay, and so that would make the radius 2. And so I drew two circles of exactly the same size. Okay, now, so here goes. To find the area inside of this one and outside of the other one would be like to find all this, right? Okay, yeah, so I hope we can agree with that. Agree with the graphs, we can agree with my picture, we can agree that we're trying to find this shaded area. Now, that's the area radially between those two curves. And it seems like you would need angles like so. Theta is this angle up to theta is pi over 2, right? So we know this one's pi over 2. This one, I think it's probably 30 degrees. I did draw this perfectly. Yeah, so 30 degrees, pi over 6. Now that would get you, you know, this wedge, those angles, that would get you half of it. The other half's the same. So we could set our boundaries like so and do doubling because of symmetry and find all of the area. Okay, so let's do like that. Okay, so the area that you see pictured up there would be the integral within the angular bounds pi over 6 to pi over 2. Okay. So double. Almost forgot. I'm going to double it because I'm only getting half of it with those boundaries, pi over 6 to pi over 2. But I like to use symmetry because this universal factor in these kinds of problems will cancel out if you use symmetry. So 1/2. And then what was the formula? If you wanted to find the area radially inside 4 sine theta and outside 2. So take the one that's further away, square it, further away radially. I guess 16 sine squared theta minus the square of the one that's radially closer. So that's r is equal to 2. 2 squared is 4 d theta. Okay. So that's what I get. That's my job now is to work that. Now, the 2.5, those are gone. And I got this 16 sine squared theta minus 4 to deal with. I guess as far as that goes, let's do like this. Sine squared theta, 1 minus cosine 2 theta over 2, right? If you multiply that by 16, you're going to get an 8. So let's say 8 times quantity, 1 minus cosine 2 theta minus 4, like so. And so I'll get an 8, and then I'll get minus 8 cosine 2 theta, and I get minus 4. So how about this? Let's do pi over 6, pi over 2. I'll get 8 minus 4. So I'll get 4 minus 8 cosine 2 theta. Okay. Alright, now, I guess I'm happy with that. I don't need to do anything else to it in order to get the antiderivative. So 4 theta minus 4 sine 2 theta. That'll do it, right? So derivative of 4 theta is 4. Derivative of sine 2 theta is 2 cosine 2 theta. Times 4 gives me 8. I want to do pi over 6, pi over 2. Okay, so from here, pi over 2 times 4, 2 pi. Alright, here I'll get sine of pi, which is 0. Then with pi over 6, I'll get 2 pi over 3. Right, because I get 4 pi over 6, I'll reduce it. And then this is, if I put the 2 times pi over 6, I get pi over 3. Sine pi over 3 is square root 3 over 2. So I'll get 4 times root 3 over 2, so I'll get 2 root 3. Okay. So that's where I'm at. Now, as far as this goes, let's see. I got 2 pi minus 2 pi over 3. So let's do like this. Oh, let's put over 3. So we'll get 6 pi over 3 minus 2 pi over 3. So we'll get 4 pi over 3. Okay. and then I'll subtract 2 root 3. That's going to be like adding it. Okay. Alright, 4 pi over 3 plus 2 root 3. And then some zeros, which we don't have to worry about. So that's area. And in this lesson versus some of the lessons that will come up, well, we'll measure different things. Areas, maybe volumes, maybe distances. So I want to start including units in my work. What's the significance of the number? Oh, it's a measurement of area. Okay, square units is just completely generic, like square feet, square centimeters, whatever units you wanted to use, right? But it is area. That's all I'm trying to say when I do that. Okay, so there we go. This is right there, our measurement right here. Okay, so let's do one more that's the area radially between two curves. Oh, I almost forgot. I take things for granted like this. I measured that was pi over 6. But you should know how to find that that's pi over 6. Okay? So let's say that point of intersection seems to determine what angle we need for this lower boundary. Okay? So how do you find the angle that indicates that point of intersection? Alright, the POI, point of intersection. Well, these two curves would be equal to each other at that point of intersection. Right? That's the point they share. They have everything in common at that point. So we could say, to find the point of intersection, I set 4 sine theta equal to 2. And then I extract some solution to that. Now, to solve this one, I can solve it more directly than the other one we looked at. I can multiply both sides by 1/4, and I'll get sine theta is 1/2. And then I can use, say, my calculator and do something like this and say theta is sine inverse of 1/2. And then I will find that, just as it appears here in quadrant 1, is 30 degrees. Okay? 30 degrees or pi over 6. Okay, so that's how we'll start by setting the curves equal to each other to find the point of intersection. How we extract the solution might depend on what this looks like to start with, though. This one I think is pretty easy to do. Alright? Okay. So yes, here's that one we're about to start. Calculate the area inside the curve R is equal to 6, which is a circle with center at the origin, radius 6. And above the line, R is 3 cosecant theta. Now I have like a pretty good scale picture right there. I should tell you though about that being a horizontal line. The reason I know that is because cosecant is 1 over sine. So this looks like R is 3 over sine. So it looks like R sine theta is 3. But if I were to convert from polar to x and y coordinates, R sine theta converts to y. So it says y is equal to 3. So I have here a circle, radius 6. With this outermost point there being a distance of 6 from the origin in a radial direction. And then I've got a line that's horizontal that goes through 3. Okay, so like right there in the middle. If that's 6, that's 3. So on and so forth. Okay. Anyway, so there's what it looks like, right? We're going to start by seeing what it looks like. And I want the area inside the circle, but above the line, then that would be this portion of the circle. Okay, alright. Now I need some angles that define that. So like something like this, maybe. I like to use symmetry, so that's the way I'm going to see it. Theta is pi over 2 right here. And then theta, I don't know, it looks like it's 30 degrees, right? Certainly looks like it. We could solve like we did that last one. What's it going to look? Let's do like this. Of course I could measure it, obviously. But, okay, if I want to know that point right there and the angle that takes me there, then I set 3 cosecant of theta equal to 6. That would say sine theta is a half, ultimately, because that's 3 over sine, multiplied by sine, divided by 6. 3 over 6 is a half. So theta is 30 degrees. Okay, so let's say theta pi over 6 to pi over 2. Alright, now I want the area radially between 6 and 3 cosecant theta. That's what all these points are. In a radial direction, 6 is further out than 3 cosecant theta. Okay, now we learned the setup for that. Okay, the area is double what I'm about to find, because if I do pi over 6 to pi over 2, that's only going to get me half. Obviously symmetric, double it for symmetry. These angular bounds, that wedge gets me exactly half of the area I'm trying to find. And that formula to find the area between in a radial fashion those two curves was to take the one that was radially further away and square it. That would be 6 and square it, minus the one that's radially closer. That would be 3 cosecant theta and square it. So I get 9 cosecant square theta d theta. Okay, so that would do it. Setup is complete.